So ladies and gentlemen, I guess we can get started. My name is Armagan Al-Haq, and on behalf of Waterloo Institute for Sustainable Energy, I welcome everyone. Now, before I officially introduce our guest speaker for today, I would like to say a few words about WISE. We have three core competencies: research leadership, academic credibility, and strategic partnership. And how are they related to our guest speaker today? I will explain. Our vision is simple. It is to have a clean energy accessible and affordable for everyone. Now, how can we do this? Well, we have to collaborate with research leaders like Dr. Zhong. Welcome, sir. And I'm just going to briefly introduce him. He is the Vice Director of Key Lab of Coal Science and Technology, Institute of Coal Chemical Engineering, Taiyuan University of Technology. He has a PhD in Chemical Engineering and Technology, a Master's in Organic Chemical Engineering, and a Bachelor's degree in Polymer Chemical Engineering. He was named the Leader of Science and Technology in Shanxi province in 2012. He received the Scientific and Technical Academy Award of Shanxi province in the year of 2008. Now, when it comes to the academic credibility, this is a snapshot of his research overview. The focus is on the synthesis of clean fuels, material, and chemicals from coal. Emphasis on both fundamental studies as well as industrial applications. His investigation includes the following. The first one on the list is chemistry of syngas, hydrogen, carbon monoxide, and utilization of carbon dioxide. Second one, green synthesis of chemicals and environmentally friendly catalysts. Then, synthesis of methanol and methane from syngas, carbonate and hydrocarbons from methanol. When it comes to his portfolio, he has more than 20 patents to his name. He has published more than 100 papers in international and national journals. And he has authored 2 books: Coal-Based Alcohol Ether Fuel and Methanol and Derivatives. When it comes to strategic partnership, our researchers shape public attitudes, informs energy policies, and improves quality of life around the globe. They have the power to make a difference. Breakthroughs come from collaboration with leading researchers such as Dr. Zhong. The outcome of strategic partnership leads to highly qualified professionals. It maximizes financial resources. The research share goes up. And again, the most important thing, how can we create economic and social value for the community? Well, to commercialize the research. So ladies and gentlemen, please put your hands together for Mr. Zhong.
Okay, thanks. Okay, first of all, I would like to thank Dr. Wen for your invitation and give me this opportunity to present our works. And also, I would like to say thanks everyone for your attention. Today, I would like to give a brief introduction for my work about the synthesis of coal-based clean fuel and chemicals. This is an introduction about our university, my label, and my work. Yeah, here is my position in China, and far away go to the university in Waterloo. My university is one of the oldest 3 national universities. This is Taiyuan. Now is Tianjin University, and this is Beijing University, and this is my university. It's a very old university. Our university consists 20 colleges and about 1,000 employees. And here is my location in the Shanxi province. Shanxi province is a very old province, and the Yellow River is close to cross through Shanxi province, and also have a lot of mountain and and the plateau, and also our province is so-called the one of the birthplace of the Chinese people. So with a long history, so there are a lot of historic and cultural heritage. This is a picture about our person is very attractive. In Shanxi province, we rich in coal, so the production of coal in the last year is about the 0.9 billion tons, and also we have larger coal pond electricity plant and the coke production, and also we science a lot of ammonia and urea and the methanol and anki from the coal, and also we sciences oil from coal by the FT sciences about 2 million tons. So this we spend a lot of coal. This is a picture of the coal distribution. From coal, we focus on 3 processes. First, from the pyrolysis, the thermal pyrolysis, we mainly the product is the coke, and the byproduct is the coal gas and the tar. And also, we focus on the liquefaction, use the hydrogenation to produce the liquid fuel like the gasoline and the diesel. The gasification is very important by the syngas to produce the energy and the chemicals. This is the energy, and also we can use the methanol as the intermediate to produce the many chemicals. And this is divided by the products we call the gas fuel. We can produce the SNG, the natural gas from coal, and the hydrogen. And also we can produce the syngas, carbon monoxide plus the hydrogen. And the liquid fuel, like the oil, like the gasoline or the diesel. And also we produce the chemicals. Chemicals, we throw the methanol to produce a lot of chemical olefin on the proper, and the aromatic, etc., and also cycle, and other, and also produce other like the char or the coke. But this talk, I want topic something like this. In China, we have a lot of coal, so the most products is based on the coal. This is the raw distribution, consumption distribution. From here, we know the coal is the main resources. This is the products in the last year, and some products in the later is not put into use. This year we building some plant, and all the industrial in all of the China L. Of course, because we use a lot of coal, so produce a lot of polluting. This is called substitution. If we produce hydrogen proton, we consume 5.44 the standard of coal. And also, if we use the direct liquefaction to produce the oil, we need 2.8 coal. So to produce chemicals or the fuels, we must consume a lot of coal. And this is the water consumption. So if we use the coal to produce the fuels and the chemicals, we consume a lot of water. This is also a problem, makes water pollution. And also about the carbon dioxide emission. This is also the big issues about the coal usage. This is our label strategy about the coal. First, we fundamentally research on the coal properties and the structure. Then we use the coal to synthesize and transfer so many fuels and chemicals. Based on the above picture, in our label, focus on the following 5 topics. First, about the coal sciences and the process technology. Then about the gas purification and the polluting controlling. And also about the carbon chemistry and the technology use the monoxide. And also we developed the novel inorganic porous material as the catalysis for this chemical process. And also about the clean separation technology. This is all for the cleaning use of the coal technology. This work is about my work. This is my work about reaction the mechanism of the syngas to the alcohol, either ester and etc. And also about the methanol conversion, and also the methanol fuel substitute petroleum from the coal as the methanol fuel, and also about the catalysis must be environment friendly. This picture is showing the coal use the plant to produce a clean fuel. This is more detail in my concern about the coal syngas to alcohol methyl use the natural gas, and the methanol conversion to the biodiesel and the gasoline, and then to the dimethyl carbonate to produce triphasage, and then to the fine chemical. And also dimethyl carbonate can produce diphenyl carbonate, and then go to the PEC and materials. In the following talk a lot about how to synthesize dimethyl carbonate. So my next talk is about the dimethyl carbonate. This is my next topic. Give a broadly introduce about dimethyl carbonate synthesis. Dimethyl carbonate is organic carbonate is very useful. First of all, the organic carbonate is a great chemical. It is no toxic, and easily biodegrade. And also, this material, these chemicals can use it as organic intermediate to produce a lot of other organic chemicals. Except that the dimethyl carbonate can use it as the oil additive to substitute of MTBE, and also can produce the polycarbonate instead of the physgene. That's a very high toxic. Usually, a lot of DMC is produced by the petroleum process. Use the ethylene oxide. But we try to develop this process. Use the methanol carbonylation with the oxygen by the oxidative carbonylation to produce dimethyl carbonate. This is a DMS production in China 2012. Most of produced by the transesterification use the petrochemical technology, and only a little use the oxcarbonylation. We try to develop the new technology. In the last century, any chemical developed this process use the copper chloride as the catalysis. This catalysis is suffer from the chloride loss during the catalysis process, and to form the hydrochloride. This is make the equipment corrosion and also polluting the water and the catalytic deactivation very quickly. In order to keep the catalytic activation, usually put into the hydrochloride to maintain the ratio of copper to chloride about 1.1 to 1. From this catalyst, we try to use the solid state ion exchange to prepare the catalyst. We use the copper chloride with the solid acid. At a high temperature, we can produce the copper chloride acid solid and reduce the hydrochloride. For this is very important about the zeolite as the solid acid. And we have tried a lot of solid acid as the material to prepare the catalysis. It is very good, but very good, and also they have shown, the literature have shown that the copper with one zeolite is very nice, have very nice catalytic performance, and also shown that the copper located in the site 2 have a good catalytic, and the calculation showed that the carbon monoxide insertion in this way is the rate determining step in this process. Besides above research, it is have a problem that the copper chloride still copper chloride refining process is very diplomatic, and also we know the copper chloride is subliminated during reaction and maybe block the pulp, and also the copper chloride is difficult to remove completely, so still in the catalysis. So the idea, we try to prepare the chloride-free copper catalysis. Chloride-free copper catalysis, we basically use the no chloride salt, copper salt. Here is a research result by the CuMY. This uses the solid state ion exchanger to produce catalysis. If use the liquid ion exchanger to prepare the catalysis by the carbonated solution, the catalytic activity is very slow. Why? We just introduce some high temperature activation to this process. The result is give a very high activity, very high catalytic activity for this reaction, but the consummation temperature is very high. This is because we find in the later that the copper-2 is exchanged in subcager, in realized subcager, is easily out-reduced to the copper-1. You know, the copper-1 is the active center, the catalytic active center. And also, at the high activation temperature can promote that the copper-2 migrate into the solid cage and the hydrogen cage prison. This is very important to make this material have a high catalytic, and also about the surrounding environment, about the copper-1. Then we try to improve the catalytic. We know from the copper-2 exchanged with the zeolite. After the high temperature activation, a lot of copper was moved to the small cage, and in subcage there are only a little copper. So how to handle the copper migrate into the small cage? That means keep the copper stay on the subcage. So we design this strategy. First, we can introduce some ion, some aromatic ion that through high temperature that migrate to the small cage, and then we exchange it with the solid solution, exchange with the ion to produce the high catalyst, high active. This result we see is the subcage catalyst is more. The subcage located more copper, and they keep have the high activity. So the copper content are similar among the catalysis. That's the analysis by the IAS. Have the similar copper content, but the catalytic activity can improve by the introduce the CE and the LA cations. And we also calculate by the DFT, showing that the environment, the copper active state environment have been changed. This is about the transfer stage. We find the LI is very long. And also we introduce the CS, introduce CS, that make the ratio of copper located in substage decreases, and this should be have the best catalytic. We from this have a very good catalytic activity. We still calculated by the DFT that shown that this catalyst have very long transition stage. This is because the copper surround the different way, different sides. This is about the catalytic activity, and Another strategy to improve the catalytic activity is about to produce the mesopore. Mesopore, we know the zeolite have a lot of macropore. Macropore is a difficulty, it makes the molecular difficulty to confusion, move from one side to other side. So we try to make the mesopore to make the make the reactor molecular to exit the active side more easily. This is about we treated by the oxalic acid. We find that they have a mesopore, and this is a picture about TEM. This is original zeolite. This treated have a mesopore zeolite, and we have the different. The acid is strong. The mesopore is also have a good mesopore. And this is about the silica to aluminum, the changes by the acid treatment, and also about the cup side. The cup located on the zeolite structure, and from this we see this catalyst have a very nice activity, and from the calculation, this small cage can block some bond to become the big pore. So that's a brief summary of the above research. Is that the cup catalysis prepared by the solid state ion exchange. This catalysis can provide similar environment around the active central cuprous, something like the copper chloride have shown a good catalytic activity. And also the result in the cuprous cation in the subcage of the one zeolite is the active center for the oxidative carbonylation reaction. And the copper 2 plus in the copper 1 zeolite is introduced to the cuprous cation during the high temperature activation, and also introduce other metal cations into the zeolite, not only at just the more cup located in the subcage, but also changes the environment around the active central copper. And the mesopores in the white zeolite is more important. This makes reacting molecules easily access to the active side, to the copper in the subcage, resulting in the improvement of the catalytic activity. This is about the copper zeolite. And another work, we work on the copper with the active copper. We know active copper is very nice spot in the catalysis. And also in the literature, we can use the copper chloride too, and the copper hydroxide with the chloride have a good catalytic activity, but this catalytic also suffer from the chloride loss. Chloride loss also makes the catalytic deactivation and the environment corrosion and the environment pollution, something like the copper chloride. So how to develop chloride-free active carbon catalysis, we develop the pyrolysis, use the pyrolysis of the copper acid. This is the catalysis we produced by the copper acid. From this research, this work, we find that the cuprous oxide is the main active species. From this result, they find the cuprous oxide is the main active species, and we also calculated by the DFT also shown that in the cuprous oxide, in the structure of this crystal, the oxygen is adsorbed on the surface of the cuprous oxide 111 with the oxygen vacuum defects and easy to decompose to the lactic oxygen, which is conducive to the formation of the oxymethanol species. And also about the carbonic oxide, which is the methyl oxidant, are undesorbed on the surface of the cuprous oxygen to produce monomethyl carbonate species. This is the intermediate about the reaction. This is the transfer stage. We also calculate the possible reaction route by the copper acid active carbon. Also shown that the carbonic oxide insertion is the main step. After that calculation, we do a lot of work about the active carbon, how to treat active carbon to prepare the catalysis more efficiently. So first, we use the acid treat to introduce some oxygen group into the zeolite surface. In the zeolite surface, to make the copper disperse more easily. This is a picture about the TEM. By the TEM, we have shown if we have a different oxygen group in the surface of the active carbon, we reduced different carbon particularly dispersed on the surface of the active carbon. This and make the particle is more different, and also the catalytic activity is more different. This is the oxidation stage, and the catalytic activity of this will have a different catalytic in the short time. So that's the dispersion. The copper 1 and the copper 0 species is more different, is more important for this catalysis. And also we find another interesting thing is that the initial catalysis, whether or not the initial catalysis is different, but after the long time reaction, the final stage seems to become the same. And these are use different treated active carbon. And the TPR after the reaction, the TPR shown that the something become to the same changes. This is a TM image of the TM. We find that even though the beginning, the initial catalysis have a lot of big particles and different, but after the reaction, something is changed. It's more give a very similar disperse of the carbon. So the catalysis show the same activity. This is for the long distance. For long distance research about our catalysis in the equipment with the autoclave with a high temperature. We found about 108 days. We find the catalysis stability is very good. It's very good. See, almost no change after the 60 days. The total is result in the methanol conversion is about the 12%, 12%, and the DM selectivity about 95, and also the activity is much better than the copper chloride catalysis, and also because we use no chloride as the precursor, as the catalysis precursor. So in this reaction, no chloride, so no equipment corrosion happened, and there's no environmental pollution problem by the chloride. And also, this project we're trying to put into the pilot scale about 5,000 tons per year. This is almost finish the equipment build. About the copper active carbon catalysis, conclude that the cuprous oxide was the main active species of the copper active carbon catalysis for our reaction oxidative carbonylation of the methanol to dimethyl carbonate. And also the oxygen adsorbed all the cuprous oxide easily to promote the formation of the methyl oxo species, which with the carbon monoxide adsorbed to form the monomethyl carbonate species as the intermediate. And the surface oxygen group in the active carbon is more important. It is a favor to the reduction of the carbon 2 reduced to the carbon 1 species. And also the carbon active catalysis, active carbon catalysis applied in the liquid phase. In the liquid phase reaction exhibits excellent catalytic activity and stability. This is more important the main result of us. And it is very quick. It is thanks acknowledgement. First, we thanks our colleagues. This is most of our colleagues in my label, and also this is collaborate outside my university. Most of them in the company, and also thanks to my student, PhD student, and master student. They do a lot of work for this research topic. And also this is my group, my student, and my colleagues. And finally, Very important, I want to thank my financial support from the government. This is the central government, and this is about the National Nature Science Foundation of China and our local Science and Technology Department. They give a lot of support on this research work. And we also research this company. This company is very interested in this reaction. Also give a lot of financial support. We would like very thanks. And also we thanks everyone for your attention and give us opportunity to present my research work. And also this is my contact information. And we hope everyone have a chance to our university and welcome to visit our university. Thanks. The copper, first, the copper is a very interesting metal. In the most of cases, the copper is very easily take place about the unreduced reaction. So if we put the copper, not only the copper 2, and also copper 1, if we enter the high temperature, give a high temperature process, the copper value state may be changed. Copper 2 is easily changed to reduced to the copper 1 and the copper 0, copper 2. And also if we enter different for example, if we treat the copper chloride, copper 1 chloride at a high temperature, maybe have some copper 0.
So that means you think the temperature is
Temperature is read and also about the environment.
Environment is the size is the reason, or is the environment have other element influence this?
Yes. The environment in their light have a different group, and also we find in the active carbon. You know, active carbon is more complicated, have a lot of different organic group. This is a symbol. This is our label. This is our label called Science and Technology. This is about the code, so we need the file and make it clear. Yeah, this is my key label, the symbol. It's long.
Research institute, right?
Yeah, research in the core. This means about the core. That's core. That's the black.
Any more questions? Okay, so now it's my turn. I would like to ask a quick question to you, sir.
Okay.
When it comes to dimethyl carbonate synthesis, how big a facility do we need, and what is the approximate cost for that facility?
Sorry, slowly.
Well, yeah, like you talked about dimethyl carbonate synthesis.
Yes.
So what kind of a facility do you need in order to do the synthesis?
Firstly,
In terms of the size, yes.
yes, we use. You mean about react equipment, right? We use the fixed bed. We use a fixed bed with different volume about the catalyst volume we put in, and we also use the autoclave at the high temperature. We use mainly two different. First is a fixed bed tuber reactor, and another is about the autoclave, the vessel as a reactor. So in the later we find the liquid find the liquid reaction is very nice in the autoclave, into autoclave.
Okay, so I guess it depends on the volume.
Mm.
Okay, perfect.
Okay.
So if we have no more questions, then we can thank Dr. Lee for an engaging talk. Sir, thank you so much. We really appreciate your time and consideration.
Okay.
Thank you.
Okay, thanks.